Hello, I'm Mr. Troha, and we're going to get some astronomy notes on spectrum and spectroscopy. So here we have a picture of the visible light spectrum: red, orange, yellow, blue, indigo, violet, Roy G. Biv, and we're going to talk about it and how it's related to astronomy. So the thing about stars is we aren't able to go to them and get any of their material and test it, so we have to use the things that they send us, which are the electromagnetic spectrum. So that's visible light as well as all the other forms of light, ultraviolet, infrared, and radio waves and so forth. So I want to talk about the tools we use to investigate those. So what is the spectrum of light? Again, for us, the visible light is very important, but there's a lot of other types of wavelengths and frequencies of light. And so any electromagnetic wavelengths we're either getting from a source of the energy, stars, lights, fire, things like that, or it's reflecting off of something and we're getting it from the reflection. Now by spectrum, we're talking about a distribution of energy that is emitted by one of these sources of light. Now, as far as the sun goes, the solar radiation comes in, it bounces off of our atmosphere, some of it's absorbed in the atmosphere, some of it is absorbed by clouds, absorbed by the surface, reflected by the surface. This graph here in the bottom left, that shows us what the largest amount of the different wavelengths are. So we have ultraviolet, the visible spectrum is a lot of light that we receive, and then the infrared also. So let's talk about a spectrograph because that's what we're going to use in astronomy. A spectrograph is a way of looking at the spectrum of light, the visible spectrum in this case. And when we get light coming from the sun or from a radiant source, if it's a hot, dense source, it's going to be a combination of all the different colors. We call that white light. But we have devices that, like a spectrograph or a prism, you may have heard of, that have the ability to separate that white light into the different wavelengths of the colors we see. So a prism does that by refraction, by bending the light. And a spectrograph, we typically use a diffraction grating, which is basically very thin slits, vertical slits, and those tiny openings allow the light to pass through, and then it bends around the edges. So if you can imagine a river and it's flowing water and you put a barrier there, it's going to pass through, but on the other side you're going to see it's not just going to be a straight line through, it's going to have kind of ripples coming off of it. So it bends around the corner. That's what light does as well. You just have to have much, much smaller openings for that to happen. There's also a picture of a CD or a DVD there, and that's showing a reflection grating. It does the same kind of thing. It's able to separate white light into its colors. So what are things we can learn? Well, we have the continuous spectrum, but depending on the source of the light, you might get some of the colors might be brighter, or maybe they're missing. So we're going to learn about that. When we read a spectrum, if you notice here, there are some missing colors, and some might be a little bit brighter. We can put that through a computer, and instead of trying to look at it visibly, the computer can analyze where the wavelengths are or frequencies are a little bit stronger. And so you see in this middle graph here, there's peaks for where it's getting more of that. And so then we can analyze what that specific wavelength or frequency is. So each object that's radiating this light, or maybe sometimes it's reflecting off of another object and passing through an atmosphere, when we see those and we see these different colors that are highlighted, they're kind of like fingerprints. They tell us what specific chemical element or elements are there in the atmosphere or coming from the star. For example, here's hydrogen. There are two types of spectrum that we look at. We look at either an emission spectrum. This is when a source is sending off specific wavelengths, like in that case, or an absorption spectrum. And this is where you have a continuous spectrum that passes through something like hydrogen, then the hydrogen absorbs those colors. Here are a few different elements. Again, they all have their own unique fingerprint. You have hydrogen, helium, sodium. As you see, as we get into more complicated atoms, we have oxygen, iron. Those have many, many different wavelengths and colors. So these lines that we're talking about on a spectrograph, these, like I said, they're kind of like little chemical fingerprints. When we have something where it's a continuous spectrum and there's colors that are missing, we call that an absorption spectrum, and those are absorption lines. Again, well, and usually they're called lines because the spectrograph that we're looking through has a little rectangular opening, and so that's why they turn out to look rectangular on our graph. So that's the absorption spectrum. We have absorption lines, and then again the emission spectrum is when it's being produced by a source of that chemical, and we see only those specific lines there. So why does this happen? Well, each chemical is made up of an atom, and each one of these atoms has a number of electrons that are rotating around the nucleus. Each one of these different chemical elements have a different number of electrons, or they're in a different configuration as far as what energy level the electrons are on. So the higher the energy, the faster the electrons are moving, and the farther away from the nucleus they are, because the nucleus is holding them in using electrical and gravitational forces. So the more energy they have, the farther away they can go. Electrons can actually jump to other energy levels, or they can fall back down to their ground state or their original levels. Thing is, they can't be everywhere all throughout space. There are specific levels that they are at. So what happens is when they absorb energy, they can absorb energy in the form of light or heat or some other things, and that causes it to jump out to a further energy level. And we say that they get in an excited state when that happens. But when that energy goes away and they drop back down to their normal ground state, then it releases that energy. And that little packet of energy is a photon. We think of photons as light, but remember, light can be everything in the electromagnetic spectrum. We're mostly interested in the visible light, though. We talked about photons. Photons in the last unit, where the sun, during its nuclear fusion, it produces energy in the form of photons, and those photons take a long path to get to the surface of the sun and eventually to us. But those little photons are packets of energy. They're specific amounts, and so we call those specific amounts or sizes quanta. And so you may have heard of quantum physics or that term, and so that's where that comes from. It's specific sizes or specific amounts. So if we were in the classroom, I would give you a spectrograph and have you look out at the sun or maybe at an incandescent light bulb, and you'd see this continuous spectrum. That's what you get from a hot, dense object. But if we were looking at, say, a fluorescent light bulb, just one of those long white ones that tubes that are usually in the ceiling at schools, then you would see you'd kind of see a spectrum, but you see certain lines that are brighter than others. If you look at one of the newer ones, or an LED type bulb, then you're going to see very distinct colors. Now, interestingly, and you should remember this maybe from freshman year, that white light is a combination of red, green, and blue. So if you look at these newer bulbs, they've actually eliminated and only used specific chemicals or specific configurations that only produce that blue, that green, and that red. And so depending how much of that is produced, that's how much looks more natural to us. So I talked a little bit ago about absorption and emission spectrums. So this is a great graphic, and this kind of sums up a lot of it. We have this hot, dense object, and it sends out, if we were to look at the light straight from that, we would see a continuous spectrum. Whether we use a prism or diffraction grating to split that light, it would turn into a continuous spectrum. Now, if we were to look at that light after it passes through a cloud of some kind of chemical, maybe it's an atmosphere, maybe there's some cosmic gas, then that gas would absorb some of the energy and into the electrons of that cooler gas, and we would see some of those chemical signatures missing. But say we were off to the side of the gas and the star made that gas glow with some kind of light. And so we were seeing it come straight from the gas and not passing from the star, then we would just see the emission spectrum lines. So what do these spectra tell us? They tell us four main things. They can tell us the temperature of the object, the composition, is it moving, and is it producing magnetic fields, or is there magnetic fields involved? Temperature is related to color, and that the higher the temperature, the higher the energy is. And in the way of wavelengths, the higher energy in the visible spectrum is the violet, blue or violet side. It has a shorter wavelengths, higher frequency, and higher energy. On the other side, the longer wavelengths and lower energy is the red and infrared. So depending on the color that we are seeing or the wavelength we're seeing, that's going to tell us how hot or cool the object is. This is an interesting graph. I thought this was really cool. We have temperatures that are associated with some of the different colors. So they were taking pictures of the sun using different filters, specifically trying to identify different wavelengths of light based on temperature. And so notice that it's more red at the lower temperatures, and as it goes up, you get more of the blues and the violets in the higher temperatures. Now, we already talked about this composition based on what the chemical signature is. The emission or absorption lines that we see, that will tell us what chemicals are involved. So the one thing I have to be aware of is it coming from the source, or is it passing through a cloud and we're getting some of those things from the chemicals from that cloud of gas or whatever, or atmosphere maybe. How do they tell us about movement? There's something called the Doppler effect or Doppler shift. And so you may have heard of a red shift or blue shift. This is most seen when we're on Earth in the form of sound. If you hear an ambulance, or if if you go to a racetrack and you hear things moving towards you, it's higher pitch. It's like, and then as it passes, it goes, and so we see this higher pitch. The wavelengths are closer together when they're coming towards you and farther apart when they're going away from you. Now, the source is creating the same wavelength, but it just appears that way to the observer. So in our case, if you look at the graph above, if we were in a lab and it wasn't moving, it would look like this. But now, if the object was moving, those lines would be shifted slightly differently. Clearly, it's the same element as the one above, but things are shifted a little bit further over. So when the thing is moving away from us, we say it's red shifted, like in this diagram. Here on Earth, it would look like this, but it shifted more towards the red side of the spectrum. If it was moving towards us, it would be shifted towards the blue side. Now, they don't call it a violet shift because just beyond violet is ultraviolet, and if it shifts off of violet, then we don't see it anymore. So blue can still shift into violet. And last thing, spectra tells us about magnetism. The way that we can see that is, notice on this spectrograph, the magnetic fields can cause those lines to divide and split into thirds. So obviously you have to be be able to zoom in and see that very well. We couldn't see that with our naked eye. So that's our information about spectrums and spectrographs. These are the tools that astronomers use to discover what stars and planets, the chemicals are out there. So hope you enjoyed.